The divergence. If we have a vector field, f of x, y, z equals mi plus nj plus ok, and the m, n, and o could all be functions of x, y, and z, the gradient was a vector field. And this could be any vector field where we have a vector as a function of position. So every position in space could be assigned a vector, for instance. One example is a gravity field. If this is the Earth and you're in outer space, doesn't matter where you go, there's an inverse square field that attracts you to the Earth. And every position would have a force attached to it. That's one example of a vector field. What's called the divergence, which we call del dot f, we actually take this partial operator, kind of looks like a vector, we dot it on the scalar components of this vector. And this times that gives us this times that gives us that, this times this gives us that. If things seem a little bit suspicious, well, they are. First of all, we don't multiply this partial times that. We apply this partial operator to that and get this. And same thing with a y partial, same thing with a z partial. So we're not following a vector convention. And this is not even a dot product because this partial operator is not a vector. So don't carry this too far. It's just a device. It's a sloppy device to help you remember how to figure out what the divergence is. This is also called div f, which is probably better notation. So this is sloppy physics notation that the physicists developed, but is actually very poor. So. But in any event, we end up with three partial derivatives. We add them up. The divergence operator takes a vector and produces a scalar. Notice there's no I, J, and K in our answer. So if you're asked to find the divergence and you have an I, J, or K in here, it's just flat out wrong. Okay. So it's like asking the speed and answering it in dollars. Okay, it just makes no sense. In terms of what the divergence is, it gives us something called flux density or flux per unit volume. We're not going to carry this too far right now, but in a few days we'll talk about the divergence theorem. In the divergence theorem, we'll actually be able to see this in action once we work through the nuts and bolts of that theorem, be able to see intuitively what it means. So here's an example. F of x, y, z equals xi plus yj plus zk. So for instance, f of 1, 1, 1 would be 1i plus 1j plus 1k. This is what's called a radial field. All the vectors point away from the origin. You can go in any location. The 1, 1, 1 would be right about here, for instance. If you move further away, the vectors get bigger. If you move closer to the origin, they get smaller. And at the origin, of course, it's just a point vector. So they change directions with location. So you can go down here in the negative z-axis. For instance, at 0, 0, negative 2, it points downward. And so that's a radial field. Well, we can find the divergence, del dot f. We're not going to necessarily plug into this convention here. We just take the x partial of that plus the y partial of that plus the z partial of that, and we get the partial of x is 1 plus 1 plus 1, which is 3. The fact that that's positive tells you for any unit of volume, you have a positive flux. This is what's called a source. You can take any little cube and basically the net flux is outward through the surface. If you were to reverse this, negative, 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 all these vectors would point toward the origin and it would be what's called a sink. And we would get a negative flux. So the net flow through the surface is inside, is from the outside into the solid bounded by that surface, and that would be called a sink. So here's another example. Let's suppose we have f of x, y, z equals yi plus xj plus 2k. And del dot f Notice you can put an arrow over F, but we don't put an arrow over the whole thing. If we put an arrow over the whole thing, we indicate we get a vector for an answer, when in fact we get a scalar for an answer. So, well, we want to do partial with respect to x of y plus partial with respect to y of x plus partial with respect to z of 2, and you'll notice these partial derivatives are all 0. So our flux density is 0. The net flow, you can pick any little surface, and you can picture the surface being a cube. You can put a cube anywhere, and basically the net flux through that surface is going to be 0. What comes in one side will go out the other side, and there's neither a source nor a sink at any location. Sometimes it can vary, it could be a source over here and a sink over here, but this is consistently neither. You could take a cube, we'll do this later on with a divergence theorem. You take a cube, which would have 6 faces. You could calculate the flux through the 6 faces, add it all up at any location, and you would get 0, quite simply put. So, okay, that's the divergence. We'll be back with a curl. This is just a general introduction. We can't cover everything in a general introduction. We could potentially teach a whole course on these vector operators and what the physical characteristics are and what the uses are. So we'll be back with a curl shortly.